Welcome to the afternoon sessions of the graduate school. My name is Ruben Wiersma, and I will talk today about deep learning on meshes and point clouds. And I'm a postdoc at the Interactive Geometry Lab in Zurich with Olga Sorkin-Hornung, and she says hi to you all. So, first of all, I guess I want to get a bit of an idea of who you are and what your background and interests are in deep learning on meshes and point clouds. So, let's try and get a bit active. Raise your hands on the following question. So, who of you have ever used a deep learning model? Okay, I see some of you are lying because most of you have used ChatGPT, and that means you've used a deep learning model in some way. So, good practice. How many of you have ever trained a deep learning model? Okay, so quite a wide knowledge of this. How many of you have implemented geometry processing algorithms? Okay, good. So who of you is excited about progress in AI? And who of you is intimidated? Very honest, good. So the goal of today's course is to sort of provide a map of the deep learning on 3D shapes. And the way I thought about creating this is, you know, these towers in Zelda Breath of the Wild where you go stand up on the tower and you open up a piece of the map. That's kind of the idea behind this course. So that you have some ideas of where are the key points in this world so you can then go and explore it yourself and go figure out all the neat nitty-gritty details. And with that kind of map, then I hope that you will be able to apply deep learning to 3D tasks. So maybe you have a task like correspondences or functional maps, and then you can use or find the right network to use this with. Or maybe you are thinking about developing deep learning techniques for 3D tasks yourself, and then hopefully this gives you a sort of some ideas of the basic concepts that are in there. You as an audience, what I expect is you have some familiarity with optimization or machine learning, which given your responses just now, you have experience with that, so that's great. That means we can start. But it also means that I will go over some basic fundamental concepts that maybe you've seen before. I hope to give some perspective on it from maybe a geometric perspective of 3D, that there's still something new in it for you, but it gives a story that hopefully connects to all the points that I want to make about 3D deep learning. So first of all, why are we interested? And I know most of you are probably familiar with all the sort of success of deep learning models on working with images to be able to segment and classify shapes in images and give us very accurate results, better than the ones we used to have with maybe classical algorithms. And the idea is that we don't necessarily want to work with 2D projections of these shapes, but with the actual 3D geometry. To be able to classify these shapes maybe, or to segment them into parts, that if you have a robot that wants to find where the handle is of the cup, it's able to segment this. Or as we saw before, maybe you have two shapes from the same class and you want to find the correspondences between them to maybe map textures between them or to find or to do registration. Now it's become more relevant and easier to do this on large amounts of data because we have access to 3D data and it's becoming cheaper to capture. So we've seen a huge increase in capabilities for image models because there's so much image data, and hopefully we're going to see more 3D data as well because of the wider accessibility of 3D scanners in both professional hardware that's getting more accessible, but also consumer hardware that's getting more 3D capabilities. That data then comes in the form of things like point clouds here for cars, maybe for internal scenes. This is the S3DIS data set where they scanned the Stanford offices with this RGBD scanner. It's actually really fun if you go into these scans and you move through some of the office of the graphics people, you can see some of the film posters from like Pixar movies and stuff. So it's recommended to check out the data set and really go into it if you like. Aside from point cloud data, of course, we're also interested in applying this to meshes. So, for example, for these correspondence tasks. And also in other domains, like medical data, where maybe we want to apply some phenotyping on bones, or we want to accelerate simulations. Here's an example of a paper where people try to approximate simulations of artery veins to estimate the stress on these artery walls, given just the geometry of this shape. Now, we as geometry processing people might think, but we already have really great tools at this and they're very accurate. Why do we expect deep learning methods to improve on this, maybe the same way that classification was improved with deep learning? And I think this is a type of case where it's a little bit of a different type of application. So the motivation behind here is, yes, we do have very accurate models that probably can do the very best, and we don't expect deep learning methods to necessarily do better. But the application here is maybe you have a patient coming in and you want to have a fast prediction so they can have some results from their scans early on, and then later on you can run a longer, more accurate simulation. So lots of applications are also in a way to sort of approximate and accelerate existing techniques. You see this as well for things like clothing try-on. You see it in games where people accelerate classical geometry processing things by training a deep learning model, almost as a kind of lookup table. So these are some of the reasons why we're interested, to be able to classify, segment, register, surface reconstruction, speeding up some classical geometry tasks by approximating them, and of course, recently a lot of interest in generative modeling. Now the difference with these techniques that we've developed on images and that worked so very well is that we now apply them to a 3D curved domain if we're not working within voxel representations. And that means that we have to work with irregular samplings rather than a regular grid. We're not working on a flat domain, but a curved domain, which means the metric is changing over our input domain. And we're missing things like consistent coordinate systems. So on images, we always have up, down, left, and right, whereas on shapes, often we work with local coordinates, which we call charts. So this is some of the challenges of transferring these techniques to 3D data to be able to do all the things that we want to do. Now let's first start with some of the very, very basics, and for these I'll sort of start with just some assumptions that maybe some of people are really not familiar with machine learning at all, just covering some of the basic concepts. So, of course, deep learning is a machine learning method, where classical approaches you would write an algorithm where the input is maybe some shape and the output is some label. And our focus would be on writing this algorithm itself and configuring all the steps that need to happen to do the tasks that we want. Within machine learning, what we have is a data set of examples of the tasks that we want to do. And the thing that we write is the training process and the model that then takes in this data set and predicts or gives us predictions for new samples. So rather than working on the algorithm itself, we work on a method to train a model given a data set of examples. And these examples, let's give them labels. So our data set, we would call the inputs X and the outputs Y. Those are the labels. It's good to note because often in optimization, the X is the unknown that we're trying to find, but here the X is actually the input. The model that we try to estimate that maps from X to Y will label here F. The parameters that we try to find, theta. The process of optimizing this model we call training, and then the model that we have optimized denote with optimized parameters, theta star. Now finding this mapping is kind of like fitting a function to data points. So in a very simple case, X might be just one-dimensional, and we try to find the line that fits these points. So here it could be a cosine, and the function f that we try to find needs to be parameterized to fit these points. So what we can do is we can measure the difference between the output of our model and the data samples, the labels, sum this over all the points in our data set, and then we try and find the parameters of this model that minimize this energy. So if you're familiar with optimization, this is very simple. It's just optimizing, minimizing an energy. But we have different names for this within machine learning, which is, this is often called a loss function. The function that we try to fit is often called the model, and then this process of optimizing people call training. So here again, theta are the unknowns, not X. Now the thing that makes deep learning specifically deep learning is that this model is nonlinear, and that is to be able to fit our data better. And that means that rather than having like a linear optimizer that we're very familiar with in geometry processing, we often do some numerical optimization, like maybe gradient descent, maybe some Newton's method, all those types of methods we could use on a nonlinear model. Second is that our parameter size is high dimensional. So we have a lot of parameters in a model that we need to optimize, which means that we cannot use optimization methods that require a lot of memory. So that means we often use gradient descent instead of maybe some higher order methods. And another part is that the samples in our data set are often huge. So we're talking about billions of input samples, which means that computing this loss function takes a lot of compute if you want to do it over all the samples. So what people do is they take samples from this data set every time. That gives them an estimate of the gradient when doing gradient descent, and that's why we call this stochastic gradient descent. So these are all some of the components that we use within deep learning that maybe aren't necessarily all ideal, but they are the things that fit to the types of models that we use and the types of data sets that we work on. So let's characterize maybe what then makes deep learning deep learning. And I would say that it's characterized by the data, the model, the optimizer, and supported by the hardware that we're able to do this on. And deep learning, I would say the big successes that we've seen are often training on large data sets. The models that we use are nonlinear and layered. We have a high number of parameters. And the typical technique is to do some end-to-end learning. Then the optimizer that's used with it often is gradient descent. These gradients are computed using backpropagation. And all of these parts were developed before. Like they were around in the 70s and maybe even before that. What allowed them to work at scale and to be able to be accessible to researchers is the availability of GPUs and parallelized hardware. Now, I'm saying all this because I think it's good to be aware of the reasons that deep learning methods work and why they're so successful, to be able to consider how we apply them to deep learning tasks in 3D. To understand, okay, what are the characteristics that we want to transfer rather than just blindly copying maybe gradient descent. I think the philosophy that some people have behind this, and I'm putting it behind quotes because this is somewhat subjective, is the idea that scaling tends to beat algorithmic complexity. So that is some of the idea behind it is as long as you have a large enough data set, you don't need to necessarily work on complex algorithms as long as the algorithm scales broader. I'm saying this to sort of explain the context of where the strategies that people go on this. It's not necessarily dogma or something you need to follow, but I think it's helpful to understand these types of thoughts behind why people do the things they do in deep learning. So that means if you have a small data set, does it make sense to work with a deep learning technique? Maybe it doesn't. Maybe you actually need a model that isn't so complex. Do you really need the complexity? If you have a linear model in a small data set, do you need a gradient descent optimizer? No, of course not. There are better optimizers available. And I'm saying all this because you see in the literature that people sometimes transfer steps from deep learning that aren't necessarily fitting to the tasks just because these are the tools that are now available. But I just want to stress these are not necessarily the ideal tools. They're ideal in combination together with these larger data sets, nonlinear models, and then these types of optimizers. So a tip, if you want to learn more about numerical solvers, Justin Solomon's book, Numerical Algorithms, is really good introduction on understanding better what solvers, what type of optimization fits your problem. Another perspective, just again on this meta perspective, is I like the talks by Alyosha Efros, and I think he's been doing this for a long time. This video that I'm linking here, and I'll share the slides there also. The URL for the slides is at Ruben Wiersma Deep Learning. You can click the link there. His point that he's making often with deep learning is that he says really it's all about the data. So the success that we see, if you have a large enough data set and you would use maybe a nearest neighbors on this, a lot of the tasks that seem like magic to us would still seem like magic just with nearest neighbors on a large enough data set. And this is, I think, a good perspective to keep in mind to really credit where credit is due. So if you have a large enough data set, something simple might work, and maybe we don't need to credit the algorithms that scale over this data set with too much intelligence. But again, this is one perspective on the situation. There are other opinions on this, of course. All right. So we have now this characterization, data model optimizer hardware. Let's take a look at some of the models that are typically used. So the typical models that have now become sort of prevalent and a lot of people use are the multi-layer perceptron, convolutional neural networks, and transformers. And I'll just build up from the very basics and then construct from that how you apply these techniques then to 3D data. So the multi-layer perceptron. So say you have this data set again, and you have labels. Inputs are x1 and x2, and they're labeled with -1 and 1. And we want to find the model that maps from our inputs to these correct labels. So one way to do this is just to separate these points, and we can do this with a line, right? This line you can encode, or you can characterize with the normal of the line and the distance of this line to the origin. So how do you then use this line to classify points? Well, what you can do is you can take the distance to this line or plane, which you can compute by taking the dot product, project all the points onto the normal, subtracting the distance to the origin, and then we could apply a step function to this distance function to give us the labels that we want. So that could be the step function that says everything above 0 becomes 1, everything below 0 becomes -1. Now within machine learning, we would call this an activation function, and there are many different options. Perhaps here we used the sigmoid function at the top left to give us the labels that we wanted. And it's important within these types of models that this function is nonlinear in some way to be able to model nonlinear functions. Now, we don't call this normal and distance, but weights and biases within machine learning. So let's replace those, normal with W and D with biases. And the dot product I'm going to write as W transpose X plus the bias. Now, what if you want to have more than one output? So now there's not just one label, but there are multiple labels. Well, what we can do is we can just simply stack these W's into a matrix of W's, which if we matrix multiply X with it, we get a vector Y out of it with multiple outputs. And of course, the biases also become a vector. And we would call these multiple outputs channels. What if the data set that we have is not linearly separable? So this component just is one line that we separate space with. Well, what we can do then is we can stack multiple of these layers of these operations, compose them into multiple layers that we now call. And this is the basic multi-layer perceptron. So this is the neural network that you know. Often you see it visualized as these sort of dots that are connected with all these lines, which can also be represented as this matrix multiplication, which you could interpret as splitting in half spaces. And these layers that you don't see are often called hidden layers. So just a couple of notes. All these examples are in 2D just for simplicity of illustration, but of course X can be of any dimension. So it can be three-dimensional for color, it could be the size of an image, it could just be any dimension. And we now discuss this interpretation of cutting up space with half spaces, which I think is a nice interpretation to think about in 3D space. So that's also one interpretation behind representing shapes with multi-layer perceptrons, is it's just a way of cutting up your space into chunks of space. It's not just one, it's not the only way to interpret these, because another way that people tend to interpret multi-layer perceptrons as universal function approximators. So that you can think of that in a similar way that you can use a Fourier transform to approximate any function with just a Fourier basis. Here you have a couple of parameters within your neural network, and we have some guarantee that it can approximate a function within a certain limit of error. But the nonlinearity for that is really necessary, because otherwise you could compress all your layers into one matrix multiply. One note as well is that with the higher complexity, you can fit closer to your data points, but it also might mean that when you interpolate, you've been overfitting. So that means you this function that we had at the sine before, if you're overfitting, you could have very noisy sine output, which is a risk of overfitting, which is more error. So how would you apply this multilayer perceptron on images? So we have this image and we want to classify it with a label, maybe A, and our function f here is this multilayer perceptron. So one way to do this is we could cut up our image into lines and just stack it all into one vector, which would be x here. And going back to this image here, every point here would be an image, and then the xi are the pixel values, but then very high dimensional over the number of pixels in your image. Now, what would be the problem with this approach? Why should you not apply this to input images? So the problem, of course, is one of them is not very efficient. So this vector x of input images would be width times height, which means our weight matrices are width times height times the number of output channels that you want. And if you have an image of maybe 1,000 times 1,000, you're going to have huge weight matrices. So that's one part. And the other part is that our patterns can be anywhere in the image. So maybe these, like the black dots of the A, maybe the A was somewhere else in the image, right? Maybe it was shifted a little bit to the right. And that means all our values are also shifted in this vector, which is very difficult for this multilayer perceptron to account for because the dimensions basically permutate. So this is where the convolutional neural networks come in. What we do here is we take the operation of convolution, which means we have an input signal and a kernel. We multiply it in the same locations, aggregate, and that gives us the new value. We do this for every point in the image, and that gives us an output image. Here it might be filtering, finding edges. And the thing is that we optimize the kernel weights. So in the model that we apply, the parameters are the weights in these kernels, and the operation that we do to apply to them is convolution. Benefit here is that we share weights, so it's much more efficient than this multilayer perceptron on the entire input image, and we have things called translation invariance. Then we often denote these as these sort of 3D blocks where the channels are the depth of these blocks, and you often see figures, diagrams like this, where we stack multiple of these convolution layers, use pooling, which means downsampling to smaller sizes to average and take sort of averages of these features. And of course, you're probably familiar with these types of visualizations where we've observed that deeper inside the network, more sort of levels of abstraction sort of are found. The patterns are sort of constructed of multiple layers of abstraction. So couple of notes on this. Interpretation of this is that you can think of this as the multilayer perceptron, but then on patches. So you just cut up these small patches, do this approach where you stack them in a pixel. That's one way to interpret this. Another point to make is that here a consistent pixel grid really helps, partly because we have the same orientation everywhere. So if you take a photograph, often the photograph is taken in the same orientation, and that means you have some consistent pattern that you can identify. That is not necessarily the case for things like medical data, where you might take a photograph of a cell or of some maybe some organism where there isn't a specific orientation. Then you're not able to rely on these orientations, so you need to work on some other types of techniques like equivariance to work with that. And of course, this pixel grid maps to hardware well. Now, a downside is that this template here is fixed. So we have this template where we have the positions already fixed at each level. And of course, we can change the values of each kernel cell, but it really only depends on the location in the kernel. And can we actually adapt this kernel to the signal itself? So not only based on location, but to the signal that it's applied to. So let's give an example of what I mean with this. So this kernel here, I'm going to call the center point of this kernel I, and all the other points j. And here we say this is maybe a Gaussian kernel that really only depends on the distance from the central point. Now, if you convolve this with an image, then what you'll see is you just blur the image, right? So very simple isotropic blur. Now, what if you want to preserve things like edges, or you want the direction of this convolution to be towards one direction? Well, one thing that you can do is you can use something like a bilateral filter. And a bilateral filter, maybe you're familiar with this, doesn't only take into account a kernel based on the distance, on the position, but also takes into account the values of the signals themselves, right? So we have this function here, f, that is applied to the pixel values, looks at the difference, and then weights this aggregation in the convolution with that as well. And when you apply this to your image, you see that it blurs in some directions, but also retains features like edges. And that's because it was looking at the difference in pixel intensity. So maybe you see the, yes, I do have this part here of the horn. There is a big difference from white to black. That means this difference is high, is large. If you had a Gaussian kernel, the weight is low, so there is no information being diffused across this layer. So here we see isotropic blurring with you just use locations, and if you can take into account signal differences, that helps you construct better features, preserves the features as well. And I think this is a nice perspective to understand something that is used in transformers, which is self-attention. So in transformers, what we do is we also have a concept of similarity of features. So here we have, in the bilateral filter, we have f. But if we replace this distance with a cosine similarity, so we take the signal itself, take a dot product, so that's xtx, that is kind of like this difference between points. It's kind of like a distance that you can use. And people use the dot product as one distance. People also use within self-attention other types of distances, but this is one of them. Now let's say you want a bit more flexibility to change what this distance measures. And one way to do that is to apply weight matrices to these features. So you transform the features. And then also we want this weight to behave. So we don't want it to explode, so to go really large. So one thing we can do is we use a softmax function to make sure that it's kind of a well-behaved weight function. And that is self-attention. So really it's that simple. Often these parts, the differences that we compute, we give different names for each of the features that are then computed, which is the key, the query. So the key is the center point that we want to test things with. The query is what we test it to. And then the values that we aggregate with this weight. So again, in this image of the image kernel, the key would be the center point, and then the query and value would be based on the outer points. And then the softmax function could be like this to regulate the weights. So transformers combine these blocks. So there are multiple ways that you can combine these blocks, have attention heads. But the sort of core fundamental block is this operation of using features themselves to compute weights. And what often is done is that there's some positional encoding included. So for sentences, large language models, you would have the distance from the word as a positional encoding. But on images, you might have the actual pixel location. On point clouds, you might have the XYZ location as a way to encode positional information. A benefit of this is it's highly flexible, or at least more flexible than the convolution kernels, because we can include these feature differences, and it's proven to be very effective empirically. So we have LLMs, we have vision transformers that do really well and sometimes outperforms images. One reason for this for images could be that they are able to make these global connections. But a downside is it's computationally very expensive. So you have to compute all these weights on pairwise distances. And that is the reason that often these things are applied more at a coarse scale. So on images, you would first compute some coarse features for patches with a convolutional neural network. And then you use attention for the higher level and connect all these global features. Or you only apply it locally. So let's summarize. We've seen the multilayer perceptron, this linear combination followed by nonlinearity, basic building blocks of neural networks. We have CNNs, convolutional neural networks, where we learn the local kernel. This gives us weight sharing and translation invariance. And it sort of constructs these localized features of increasing abstraction. And then the transformers, which learn weights based on feature similarity. Highly expressive, but also expensive, and the current state of the art for many tasks. So now we go to 3D data. And in this block model, what changes is rather than image data, we have 3D data. And this 3D data comes, of course, as we know, in many different representations. And the classic ones that we're familiar with are voxels, point clouds, and meshes. Now, in this lecture, I'm not going to look at voxels because the voxels is quite a direct transfer from images, right? We have just the pixel grid, but then with the third dimension. And these are very effective as well. You should pay attention to them if you want to apply deep learning to 3D models. But here we're going to focus on applying them to point clouds and meshes in case you want to work directly on the 3D surface. Now, I hear some of you asking, what about implicit functions? So these are functions where for a point in 3D, you would give the distance to the function and the surface itself, you give the distance to the surface and the surface is the level set where the function is 0. Now, in deep learning, we often use these representations, but it's often used, the multi-layer perceptron, for example, to represent this function, the sign distance function. It's not as often used to analyze a sign distance function because what you tend to do is sample this sign distance function, for example, into a voxel grid or onto a mesh or a point cloud, and then apply a deep learning approach to this. So we also won't look at implicit functions here. Now, the point clouds, of course, is a set of points in d-dimensional space. So in 3D, just a set of points in 3D. And the mesh kind of complements the point cloud by giving the connectivity of the surface with our vertices, edges, and faces. The geometry on our mesh can be on the points, so as 3D positions, but can also be given intrinsically as distances over the edges or angles between edges. And of course, within machine learning, we need data sets. So some of the fundamental data sets that a lot of people work on are ShapeNet and ModelNet. These are early data sets that are sort of large enough to start doing some deep learning. And these are often given as meshes or point clouds with tasks like segmentation and classification. So you'd have some point cloud where you want to find the segmentation into parts. Now, you have to remember with these data sets that relatively to image data sets, so where we know all the success from ImageNet classification, from diffusion models, these data sets are tiny. It's in the range of 10,000s of shapes. And you can sort of see this in the benchmarks that are happening, that they're saturating a little bit. So even if we have more complicated models, we see really small increments in what's being improved. And I think part of the reason for this could be, if we look back at this data sets models optimization, that really the data sets are quite small, and can we really expect much more on these specific data sets? But luckily, there are more data sets than this, and there are larger data sets. So we have things like ScanNet, S3DIS, Thingy 10K, of course, for meshes, ABC. And I think here it's also good just to mention that some data sets are also available that have millions of shapes. But I think it's also important to consider the ethics with the copyright that come with this, because some of these shapes were taken and scraped from places where people, like, they tell you not to use it for AI training, and people still do. I think it's great to work on things that, if it's possible, let's do it, but let's also make sure that we live in the world in the future where it's still nice to be in that world, right? So to respect people's copyright when they use it. That's not saying that I will never use this data set, because people are under their own pressure, so it's probably not up to you personally, but I think as a field we should really consider these things and take them seriously. So, what if you want, for a lot of these data sets, things are like segmentation classification. So we have some labels given, maybe for every vertex on the mesh, we have a label per vertex that gives us the segmentation, or per mesh we have a classification. So what if you have other types of more exotic things like simulation? Now here your input could be position or distance to loops. So this specific paper here uses for each point as an input feature the distance to loops, and then their output would be a tangent vector at each vertex, which gives the shear and stress. So that's a more exotic type of output, and here the output was generated or created, synthesized, with a simulation. Another example of more exotic inputs and outputs for this parametric virtual try-on. The input would be garment of parameters, the output would be mesh positions on a mean shape. And then this approach does it with multiple stages. So they then go for mesh position at the mean shape, and then have smooth mesh positions to finally go to a simulation with the fine wrinkles. So you can see that you can vary also the inputs and outputs that you train your models on specific to the tasks. Another example of different types of outputs that you can use is neural Jacobian fields, where the input here is a per triangle centroid and the output is a Jacobian matrix for every triangle. So basically a matrix that says how each triangle changes, and then we post-process this Jacobian to tangent spaces. So these are other ways of sort of creating or using data. Final note that I want to make about 3D data before we continue to the 3D models is, what if you have a bunch of meshes or you have a bunch of point clouds, but you don't really have any labels or anything that you want to train the output on? And then what we can do is unsupervised learning. Just a very quick example of what a strategy here might be is an example of an autoencoder. So here the encoder and decoder are models like this convolutional neural network. And the idea is that we train this network to have as input the mesh itself and as output the mesh itself. But there is a bottleneck included in the network. And the idea is that through this bottleneck, there's going to be some representation that encodes the important information about the shape, important features that are required to output the shape again. And then if we have some restraints on this Z, on this space, then we can also sample it at a later space. So these models might be seen as transformers, but we can sample it at a later space to maybe generate shapes. So that's one way that you can still use 3D data sets without all the labels. So how do we then apply our architectures that we've seen to 3D models? And back to this diagram, we have the 3D data, and of course now we're going to change and adapt the models for 3D, but the optimizer and the hardware often stays the same. And let's start very simple. Say we have this point cloud of a bunny, and can we just use a multi-layer perceptron on this to get features from this point cloud and then a bunny? So what we could do, maybe similar to the first idea for images, is that maybe we stack all the points into one large vector and then put that into the multi-layer perceptron. A problem that comes up is that you don't have a fixed order for point clouds. So there is not really a fixed order, so it could be that a new point cloud that you input, the order has been changed, and that means your multi-layer perceptron doesn't work again. So one approach to fix this is what PointNet does, which is it applies a multi-layer perceptron to each point, and then takes the maximum over all the points as the feature for these points. And the reason this works is that the maximum is order independent, order invariant, so that means it does work on each point cloud independent of which order you put it in. Now you could also use average or sum, any other operation that would be order invariant, but it seems that the maximum approach worked best. Now one downside of this approach is you see that we take the maximum over the entire point set after computing a feature for each point, which means you cannot really learn from neighborhoods. So consider, for example, if you want to compute curvature on an object, you need some derivative of your shape. You need some surrounding area to know what the curvature is of that object. Something like PointNet would not be able to compute this because it doesn't have any view of the surroundings. So if you expect your network to be able to learn from something like curvature, then consider what type of network you use and if it really is able to find these features. Because you can already see from how it's set up that it won't be able to learn curvature from this. And we can't expect magic from a multi-layer perceptron. Actually, a point here as well to take is that because we know these multi-layer perceptrons as sort of cutting up this space and really looking at space, you could even think that maybe some of the effect of it is finding statistics in 3D space over things. So we could sometimes be fooled into thinking that a method really works, even though it's just been doing something that we didn't expect. So let's fix this local neighborhood problem and apply a multi-layer perceptron on each point, but then take a maximum over neighborhoods. And that is what PointNet++ does. The neighborhoods you could define as k-nearest neighbors, or maybe some radius graph, which could be more robust to sampling. And for this, you could have different options, right? You could use geodesic neighborhoods, Euclidean neighborhoods. There are a bunch of papers where every paper tries a different neighborhood, but probably it's something that you want to try out for yourself, which one of the options works best. And the operation itself, we denote here with this multi-layer perceptron on the features of the points. It also takes in some positional encoding, and then the maximum over the neighborhoods. In this network, they also make hierarchies with maximum pooling, like you've seen in convolutional neural networks, and that gives us point plus plus. Now, a good thing to note, I think I'll also stress this later, is that a lot of people, even though it was like in machine learning ages, it's ancient. Of course, in the normal science, it's not very ancient, but people still use this, and what happens is that a new paper comes by, develops a new technique, and they don't only change the convolution operation, but they also change everything else. So they change the architecture, they change the training schedule, they change the data. Sometimes they add sets to the data sets. Then they compare it to point plus plus, and then they say, we've improved it. And it's understandable because there are a lot of pressures on you to publish. But what happens is then every now and then a new paper comes by that says, well, let's try point plus plus with all these changes and compare it to the other papers. And then you often see that point plus plus sort of is at the same level as these other approaches. Now, note with that is, given the benchmarks that we have and given the tasks that we have. So that's not said that some techniques, so some data sets, some tasks require more complexity and require something more than a maximum operation. It's just to say that maybe start simple if you want to try something out first. You can definitely try out point plus plus. It's a very simple operation. You can give it a try, and then you can always make it more complicated as you need. So let's take a step back and generalize these ideas from point plus plus that we just saw. And let's do that by considering the surface maybe as a graph, where all the points are nodes in this graph, and we connect points together with edges when they're maybe nearby, like a k-nearest neighbor graph or a radius graph, or for meshes, maybe we can use mesh edges. So what can meshes help with, these mesh edges? Well, an example is that because we have the connectivity on the mesh, we are connecting points that are really connected along geodesics. So say you have these fingers here that are connected very close to each other. If you were to use a radius graph or k-nearest neighbors, you would connect these points on the fingers. If you use your graph, if you base it on a mesh, then you wouldn't connect these fingertips together, and that might be helpful for some tasks that you might want to do. So that's also where you can think about, do I need to use nearest neighbor graph? Do I need to use a mesh edge? It's based on these types of considerations. So once we have this graph, we can sort of describe a lot of operations that are now developed for machine learning on 3D surfaces as message passing. And this was first sort of done by Gilmer and colleagues in neural message passing, and there's a library, PyTorch Geometric, that implements a lot of approaches within this message passing paradigm. So it's a nice abstraction to think about these operations to be able to implement them and understand them in the same framework. So what happens here is we compute a message on each node and then aggregate the message over edges. Very simple. So for point plus plus, that looks like this. The message that we have is a multi-layer perceptron on our input features and the point positions. And the passing operation is the maximum over neighbors. Now people extend this and change some variations of this. An example of that is edgeconf. So edgeconf, the message that we compute here, is relative features over edges, and the passing operation is still a maximum over neighborhoods. So very closely related to point plus plus, just computes a different type of feature, but still takes the maximum. Another well-known approach is graph convolutional networks, also very related. The message here is a linear transformation of your features, and it's passed by taking a weighted sum of these features. Now, because we're geometers in the room, we can also consider this from the perspective of our favorite operator, the Laplacian. So you can think of these operations as applying the Laplacian to your input features. So we know the Laplacian in discrete setting is the difference to the average of our neighbors. With GCN, graph convolution networks, we actually use the graph Laplacian as the diffusion operator. And with edgeconf, it's sort of inspired on this idea of taking the difference to the average of neighbors. So if you were to replace this maximum with a sum or an average, that would be like this combinatorial Laplacian as well. And that's one way to interpret these operations, is that these networks, what they do is they sort of learn to diffuse features over your surface with GCN smoothly, with edgeconf sharply. And one interpretation of that sort of maybe gives some intuition for that is like the heat kernel signature, where how you diffuse tells you something about the shape. So this gives some intuition for why these operations might be able to learn informative features. Let's add a bit more geometry to these operations, because now we just looked at a graph and did a lot of combinatorial things. And the reason that we want to add more geometry is that we often use discretizations that might be very irregular. So this bunny over here, if you were to use these graph approaches and you don't consider the difference in density of our points, then we would not be able to apply our techniques in a way that sort of generalizes over these different discretizations. And we know in geometry processing a lot of ways to deal with this. For example, lumped mass matrices or other ways to deal with different densities. So that's why we need to consider geometry in these types of cases. We also have a lot of different discretizations that we have to generalize over. This image is from DiffusionNet. I see I didn't credit it, but it's from the DiffusionNet paper by Nick Sharp and colleagues, where maybe we have meshes, maybe we have point clouds, and we want our approaches to work on each of these approaches. And within geometry processing, we have a lot of tools and techniques to have robust operators that could generalize over these discretizations. What about mesh quality? How do we consider this? These are actually very important to consider, because there are data sets where if you don't consider this, you're actually the very best method, because there are some data sets that have the same connectivity for each mesh, like Faust. If you were to train a network that is sensitive to these types of things, you could overfit on the connectivity, have 100% accuracy on your connectivity, but it would be useless in practice. So make sure that when you test these types of things or think about them, that they also work with these types of challenges we have with realistic data, and that you're not being fooled by your network that it's really doing very well, even though it's just overfitting on artifacts. A final thing that we want to consider geometry is that we want to be robust, or we want to have certain invariances and equivariance baked in. So on images, as I said before, you often have a fixed coordinate system. Not always, but for certain types of images you have this. But our 3D data, we could rotate our 3D positions in any way, and we still want it to work with our 3D models. So that's something we want to be invariant to. And the second thing is maybe we want our operations to be intrinsic on the surface. So versus this extrinsic approach where I always give this example of the difference between extrinsic and intrinsic. Extrinsic distance you would compute between points through 3D space, and intrinsic along the surface, which means that if you change the configuration of your fingers, the intrinsic difference doesn't change, but the extrinsic difference does. So in technical terms, if you have isometric deformation, you would be robust to those isometric deformations. Also, you can work in 2D instead of 3D, and you don't have distortion or inclusion. And if you want to work intrinsically, then you have to deal with different coordinate systems at different places. So maybe we also want to have some invariance of those baked in. Now, to look at how you would include all these types of features, let's go back to what we saw with the CNNs and transformers, consider that as a graph, and then see how you can apply that to our 3D data. So let's consider the CNN, but then apply it in the way that we would do on a graph. So we would have our center pixel would be this green dot, and all the surrounding pixels would be the blue dots. And what we do is a message type approach. We compute a message on all the surrounding points, aggregate them here with a sum. And that would be the operation that's convolution for images. Now let's compare that to the graph convolutional networks. And what we see there is this weight matrix that we had for images is a different one for each surrounding point, but we use the same weight matrix for each surrounding point in graph convolutional networks. So it's not considering 3D positions. So if we want to convert a CNN from images to point cloud data, how do we include the 3D position into it? Now, there are a couple of different ways that you can do this. The first is that you base your weights on the 3D position, so extrinsic 3D positions. And there are networks like KPConv. A recent KPConv-X also sort of extends it and improves it to be up to par with state-of-the-art. And what you see here is similar to the image. You have a position in 3D space, and the kernel weight is computed for each of these positions and then interpolated into 3D space using some basis functions. Another way to include positions is to think of these kernels as being applied to the surface through the exponential map. So you'd have your positional weights, maybe in a 2D coordinate system, and then you map it to the surface using the exponential map, and then that's the way that you include directionality. There are a couple of approaches to do this: GCNN, ACNN, MONET, etc. And each of them varies the kernel itself that you apply, and tries to also bake in some properties like rotation equivariance. So what you can probably already imagine is if you apply this map, there's not just one way to rotate this map, right? There's an ambiguity in how you rotate this mapping around the normal, and there are some approaches that try to fix this ambiguity or get around this. A final way that I'll treat here is operator-based, so not considering this kernel that is applied to the surface, but thinking of convolutions as this operator-based, like the diffusion Laplacians we saw before, like using the networks as diffusing information. And then one approach, delta-conv, what it does is it takes the gradient and divergence, as we know as Laplacian is gradient, divergence of gradient, applies a nonlinearity in between to give us nonlinear functions. And that also allows us to learn anisotropic diffusion and operators for a neural network to have directional information. So finally, how do you transfer transformers to your 3D data? Well, now that we have this consideration of a graph, we can compute the key as this center point, the query as all the other points around it, and the value also from all the other points around it. And here really we don't need anything to transfer. We can directly transfer this to a graph. There's nothing to it really, except, of course, there is much to it and there's work to do this. So some challenges here are, how do you reduce the cost? So if you were to apply this transformer, this attention to all the points in your point cloud, as you can imagine, that doesn't scale at all. So what some approaches do is they either apply it maybe on a local neighborhood, so they also take nearest neighbors or a radius graph. Some of them apply it on a serialized point cloud, so they put the point cloud on a line through some space filling curve or a z-curve and then apply attention to this. So that's the type of challenge that they then try to fix. So transferring the basic operation itself is not that difficult, but making it performant and making it sure that you can work on huge point clouds is, and that's the challenge. Another challenge here is that you want to have some positional encoding often. So maybe you want to be based on some 3D encoding. And then again, you have these problems that we had before with positional encodings that you still have to deal with. How do you rotate your 3D shape? So maybe you need some equivariance in there, invariances to your point positions. So the current of the state of the art is that many approaches are around and many of you can try, but PointNet often still seems to work quite well in my experience. Now that's not saying that don't use anything else, it's just saying if you want to try something, start simple and then expand on it. Other options are also often seen, so point transformer is something that I've recently seen a lot in 3ds, just something you can try, or sparse voxel convolutions. And really which one to use depends on the task that you want to do. So do you expect your network to understand curvature? Maybe you don't really want to use .NET++ because of this maximum operation. Or do you want efficiency or simplicity? Try the simpler networks first. Really, there's as I was taught in my very first class in the bachelor, no free lunch in computer science. Some methods that you really should know, but I didn't get to cover, given the time that we have, are mesh CNN. So it's a very important work working directly on meshes. Here the network works on mesh edges, and it uses geometric features as input. So dihedral angle, inner angles, edge length ratios. And this is one way to solve this problem of what input features do you use. This uses only these sort of features on the mesh. Another very important work, diffusion net, which we also saw in the spectral talk, based on this idea of learning to diffuse information along a surface and then using diffusion over time as a way to compute features. So they show in that paper that if you have a certain time that you diffuse, so say you have a heat source, you diffuse this over your surface and you set it at a certain time, then that is a good descriptor, or that can give you good descriptors of the shape. Now you could compute this diffusion by using a linear solver in every time step. That doesn't really work very well, scale very well when doing training. So what they do in this paper is they accelerate this diffusion by going into the frequency domain using eigenvectors of Laplacian. And that also makes it quite robust to different discretizations. So if you have a robust enough discretization, or discretization of your Laplacian, and you use low enough frequencies in your frequency domain, then you can learn features that can transfer between meshes and point clouds. One more note that I want to make before I show you a bit of hands-on practice is, what about this problem of rotation invariance? So I showed before this bunny that was rotating, and also in the spectral talk we saw that input features are actually quite important, and using just XYZ features, does that work? So how do you make sure that your models generalize over different rotations of your input surface or different translations scales? Well, the brute force approach would be you just augment your data. And that's what some people believe is the way to go. Don't make it more complex, your model, just augment your data, increase more data. That's from the strategy thinking of, okay, it's just the data, let's make the model simple. So you could add random rotation translation. Another approach that people tried early on was to learn the transformation from your data. So we saw this in PointNet. What they do here is they take your input point cloud, they estimate with this TNet a 3x3 transform matrix. So that's, they learn this transformation that puts it into a canonical position, and then that is fed in as input to the rest of the network. So it's a way to sort of undo the transformation and finding this transformation using a learning method. Another thing you can do is you can use invariant input features. So heat kernel signatures, what we saw on mesh CNN, so things on edges like distances. Or you can encode features in local frames. So meaning you have some local frame and then you'd have the difference in features. So point difference, maybe normals, or just distances. So these are also done in some papers. And a final approach cheating here is that you can use things like rotation equivariance. So using things like spherical harmonics to encode your features so you can have some properties of equivariance. All right, so these are then the ways that you can work. You have your 3D models. Let's do a very brief introduction of actually applying this to your 3D shapes. And I think I still have half an hour left, right? Yeah. What I want to show you is how you can set up a neural network for a 3D shape using PyTorch geometric. This is just one implementation of a lot of these networks. What I like about it is it sort of implements this message passing paradigm, which means it has a very nice abstraction layer between different approaches, and it's very easy to try different variants. So you're not stuck with like one thing because there's only one thing implemented, but you can really flexibly change things. It's got also many helpful utilities. And of course, there are alternatives to this. So things like Kaolin from NVIDIA, PyTorch 3D, which I think is from Meta and GraphGym. So there are many alternatives that you can also try if you want. Now, for this if you want to follow along, or I'll probably let you follow along later on, what I'll do is I'm going to mirror my screen. Yeah. All right. Very good. So, if you want to follow along, you can go to this URL, rubenwiersma.nl/deep learning. I would suggest that you would probably do it at home if you are interested. I'll go over it in a way that you probably won't be able to pace along. But I just want to show you sort of the steps you would go through to set up a neural network on some 3D shapes for a simple task. So what you can do is you can download the code for the tutorial here. That would give you this folder with a Jupyter notebook and a README. And I've already set up the Jupyter notebook and Jupyter environment. There are some README, in the README, there are instructions to do this. What I'll do is I'll just open up the Jupyter notebook. There we go. And when you start Jupyter, you'll see the SGB DL tutorial, which is this screen over here. Let me see. All right. I think one important, so I showed already in the sort of theoretical part of this lecture, we have this data, the model, and the optimization. And we're going to go over the same steps in this tutorial. So after we've set up the environment, what we need to do is we download our data set and process it. And I think one of the most important steps that I want to show you here is that it's very important every time that you do something with machine learning is check your data. And maybe it's something that's very simple to consider, but it's really, it will save you so many debug cycles that you've maybe set up some training algorithm, you've let it train for a couple of hours, and then you find out it doesn't work. That's because you haven't checked your data at first. So one tool that I find really helpful for that, first of all, is just, you can inspect your data sets and walk through them and just see all the classes maybe that are in the data set, maybe the couple of shapes, the positions, the shapes and sizes of your tensors. But another is visualize them. So for that, you're probably familiar with these tasks, but I really want to show if anybody's here is like a first-year PhD and you've never used these, I think these are going to be very useful for you. One tool is Polyscope. It's got both a Python library front end and a C++ sort of implementation. And you can easily render meshes, point clouds in it. Very simple, just a couple of lines of code. And you can use that just to simply maybe show some of the shapes. So I'm going to change the dataset element, and you'll see that this dataset here, ModelNet, has a couple of bathtub examples, and we want to classify them into bathtubs. Maybe we have from another class something. Oh, this is another bathtub. I think what I did is I added only 20 shapes in this sort of smaller. Okay, this is a bed. And let's take a look. Okay, if we look at the edges here, we see that this mesh is actually quite, it's not a very regular meshing of it. So maybe that already says something about how we want to process this data for our neural network, right? If we just want to use the vertices and the edges as our input graph, is that going to work? Probably it won't work very well, so consider that when you inspect these meshes. And another tool that's going to be useful if you want to work in a notebook is Meshplot, where we can also show these different mesh outputs. Something that's in the notebook as well is you can consider where your data is. That's something, if you're just very new to deep learning, it's something you have to get used to is where does your data reside? Often it's either on the CPU or near the CPU or GPU, and that's something you just want to be aware of. And the first thing to do when you have these meshes is you want to process them and convert them into a representation that will work well with your neural network. So the way that we do this in PyTorch geometric is as transforms. So what we do here is we just apply a normalization of our skill, we sample a point cloud, and we compute this k-nearest neighbor graph. So that should take about 7 seconds because I have a very small data set here. If you have a GPU or a faster computer, then you can also increase the data set size. And then this is the input to our network. So we've sampled a point cloud from our mesh. Let's try out maybe this bed example that I had before. Yeah, right. So now we've sampled it uniformly. We still see like some holes. So these are things that you can then consider and sort of have this feedback loop between, if I see an output from a network, am I expecting it to work based on what I'm inputting here? This is actually something that I see as well in things like ShapeNet. A lot of tasks are trained on 2,000 points, which is quite a low resolution to get maybe good features that we expect when we imagine, like when we imagine some of these networks working, we probably think about, oh, it's going to look at the curvatures of these shapes. But when you then inspect your shapes and you see this motorcycle with a bunch of points somewhere, can you really expect it to do very well in segmentation? Probably not. So this is a way to go back and forth between debugging what you expected to happen and seeing what is actually the input to your network. All right, then we have things like setting up, actually loading this data, sending it to your GPU. And then here we see this implementation of the point net layer with message passing. I think it's interesting just to see very quickly what we do here. So I talked about this message, computing the message, and then aggregating with maximum. We see that implemented quite directly here. We have a message function, which takes the features of our points. It doesn't do that. It's sometimes like when you shake it, it increases the size of the pointer. It takes the point positions and the difference between the point positions, so quite a very direct copy from what we saw on our slides, applies a multi-layer perceptron on it, so that's the message that we compute. And what's nice about this library is it already stacks for you these tensors of the features for neighbors in your central point, so you don't have to think about doing that yourself. And it also does this aggregation, this maximum aggregation for you, so it does that in the propagate. In a forward pass of the model, you call propagate, and it calls the maximum operation for you because we told in the instantiation of this object that we want to use maximum aggregation right over here. So that is a very simple implementation of our PointNet++ layer. What we do when we set up a network is we combine these we stack these into multiple layers. So here in our forward function, what we see is we apply a convolution, a nonlinearity, a convolution, a nonlinearity, and then a maximum pool at the end. And that is our neural network. So if you go through this, then you can program this neural network. And what I invite you to do if you want to go through this, there are a couple of tasks that I put in there, given by these arrows. You can try out maybe interchanging some of these functionalities. So maybe can you change this PointNet module to this graph convolutional network? What we saw, that's actually, if you want to use certain, let's say, if you want to convert it to edgeconv, that could be as simple as just changing this hj to hi, then hj minus hi, and we have edgeconv. So that's a very simple way of comparing these different approaches, and hopefully this allows you to understand all the literature that you see and understand how you can apply it and what you can expect from these approaches. So I've implemented it then, and then the final stage is training the model. So what we do is we set up an optimizer. Maybe you're familiar with setting optimizers for geometry processing tasks. We set up the energy function, the criterion, the loss. And then what we do is the training loop is this gradient descent iterations. And we do that for a couple of epochs. So here I did something wrong. Probably I changed something, but it works in the way that you, if you download it directly, maybe I said the edgeconf change was so simple, but actually I made a mistake there. Anyway, so once you train it, you'll see that because it's quite a small data set, you get up to like 60% accuracy, and then finally you can visualize the output. So I hope that tutorial, if you go through it yourselves at your own pace, can give you some feeling for implementing these types of things yourself, and you can apply it to your own tasks. So with that, I want to thank you for your attention and point you to the website if you want to have access to the slides and the code. You can find all of that there. And yeah, with that, thank you. Are there any questions?
It's mostly a curiosity, so nothing important. But in the code you show, the position were encoded as a matrix with all the vertices and the outer shape was 3, but the faces was transposed, the faces.
Yeah.
There is any reason for this? Does it improve the... Because it's really weird to me to have this transposition.
It is, yeah, I think that's just a library choice. It's, but it's true. That's why you have to also take care in when I wanted to visualize them, I had to transpose them myself.
Does it improve some... because are you encoding the network by matter a bit? Does it improve? Does it change things?
No, I don't think this was done intentionally as an improvement. And also so most of the operations in this library, they think of the mesh as a point cloud. So they don't think of it, because you see that if you would think of it as a mesh, you would include a mass matrix, for example, in these operations. The reason, like why they exclude it, is they often think of it as a point cloud which has been sampled uniformly, so then you can sort of assume uniform mass matrix. So I don't think the mesh representation is intentionally done this way. No. Any other questions? Yeah. Yep. So that's actually a very good question. So what if you have more different matrices? And the problem where this comes up is, say you have this maximum over your entire point cloud, right? Then typically you'd do a maximum maybe over one of the dimensions of your tensor. And if your shape is not uniform, then it's difficult to get a tensor that has these homogeneous dimensions. This library has a GPU implementation of a scatter operation, which means that it takes input as a tensor, it takes an index tensor as well, or an index array, and then it does an aggregation operation over all the indices that are the same. So say you have an index tensor as 0, 0, 0, 0, 0, and you say that the scatter operation should be maximum, then it takes a maximum over all the indices that are 0. So this library allows you to do with inhomogeneous data sets, so with different size shapes, and that's because they implemented this in like somewhat optimized manner. There are the same problem you would have for the maximum over your neighborhoods. So this is why you could prefer k-nearest neighbors, because you have the same dimension on every tensor, and you can take a maximum which maps well to your GPU. And that's also a reason why some people do this. They say it's much faster to do k-nearest neighbors, even though the radius graph might be better theoretically. But that's also something you probably have to just balance and try yourself when you want to do this. So it is possible, it might be slower. Yep.
So I'm not an expert on any of this, but as far as I know, most of the computation is done in floating point arithmetic, right? And I've heard people even do like loads of schema or something like that. Mm-hmm. So I'm curious if there's any work on like exact computation or anything like that. I mean, like represents on the exact instrument.
Ooh, good question. I'm not familiar with that, but I assume there is. There is a lot of work on different sort of representations for your neural network weights and for example, pruning it for efficiency. So maybe in that direction. But I'm not familiar with exact representations for shapes or that type of thing, no. but maybe somebody else is. So they can... All right, if there are no more questions, then thank you very much for your attention.